Hi everyone, this is Arezoo and I'm going to present on the behalf of our group on control co-design for buoyancy controlled MHK turbine and nested optimization of geometry and spatial temporal path planning. Okay, in this presentation, I first give you the background and motivation behind the work. Then I discuss the modeling procedure for the buoyancy controlled marine current turbine system and discuss the proposed framework for the control co-design to couple the physical design and spatial temporal path planning together. Then I show you the simulation results that are obtained during this study and finally conclude the presentation and give you the future works to continue the current study. Okay, so first, background and motivation. Okay, the main question here is why marine renewable energy? These are very important resources for us to reduce reliance on the fossil fuel and also improve the blue economy. There are different types of energy resources in the ocean, such as wave energy, tidal energy, ocean current, river current, and ocean thermal. And we need some types of technologies to harness this power, which are shown in this figure. Specifically, we focus on the ocean current and marine current turbine system. So we have different applications for these technologies, such as water desalination and powering disaster area, which can benefit the blue economy. But the main challenge for developing the marine renewable energy system are high cost in design, operation, and maintenance. So we need some mature research in this area. Okay, specifically for the ocean current energy, we need the integrated design process, which is necessary for a multi-layer complex system such as marine hydrokinetic energy turbines. To harness the maximum power from this system, we need the path planning algorithm to navigate the system through the water column and also consider the spatial temporal uncertainties in the oceanic environment. So the physical design influence on the controllers should be considered in our study, and we have the limited literature on the control co-design for the marine current turbine system and generally the marine hydrokinetic turbine. So we identified this gap, and specifically our presentation is on developing a control co-design for marine current turbine system to couple the physical design and cyber controller or path planning algorithm together. Okay, so we first discussed the marine current turbine modeling. We designed a 700 kilowatt marine current turbine, which is initially designed to operate in the Gulf Stream of Florida's East Coast. This is a baseline design, and we consider 700 kilowatt as a rated power for this system. This system includes rotor, main body, mooring cable, which is used to attach the system to the seafloor, and also variable buoyancy chamber, placing 2 variable buoyancy tanks. In terms of technical perspective, we have 14 states to model this system, including linear body position, Euler angle of the body, linear velocity of the body, angular velocity of the body, and 2 remaining states are related to the rotor, including rotation angle of the rotor blade and angular velocity of the rotor. We have also 2 actuators to control this system. 2 actuators are related to the variable buoyancy field fractions, which are mainly responsible for the movement of the system, and the final actuator is related to the electromechanical torque. Okay, then I want to formulate the equations of motion and model the motion of this system. We have 7 independent equations or 7 degrees of freedom for modeling this system. These equations are written based on the forces and moments acting on the system for 6 degrees of freedom for the motion of the main body, and the last degree of freedom is related to the rotor's rotation about the x-axis. So we have 5 different coordinate frames for modeling the system, including inertial coordinate frame, body fixed coordinate frame, momentum mesh coordinate frame, shaft coordinate frame, and rotor blade coordinate frame. Okay, then since we want to avoid any computational complexity in our procedure, we just want to find a linear model for the vertical movement of the system and do not use the dynamic modeling. So we find this linear model and justify this with the nonlinear model to just prove the precision of this algorithm. The first linear model is related to the vertical movement, which considers the field fraction as the main actuator of the system for the vertical movement. So any changes in the field fraction is related to the changes in the ocean current velocity and also changes in the operating depths. So we want to find these constant values, constant parameters, which are calculated based on the nonlinear model. Then the second linear model is related to the harness power from the system, which is found with a similar approach. So the net harness power from the system includes three terms. The first term is related to the produced power from the MCT, which is mainly dependent on the ocean current velocity. The second term is related to the power consumption to hold the operating depths to resist any changes in the ocean current velocity. And the last term is related to the power consumption to change the operating depths. So we just show the simulation results to justify the first linear model for the vertical movement of the system with the nonlinear model. And from the results, we can see that our linear model is almost precise and the results are similar. Okay, so now I want to discuss the proposed control co-design framework for the MCT to couple the physical design and path planning algorithm together. But the first question here is why control co-design for the MCT? We know that the path control challenges for the MCT system is intensified if we do not have a kind of efficient mechanical design for the system. So we should make sure that the planned path is qualified for the physical design, and we should consider the limitations from controllers and actuators in the path planning algorithm. So we want to have a prominent MCT design. This prominent MCT design needs harnessing maximum power from the system while it is tested to the seafloor, and also this should harness this maximum power while the system keeps the minimum weight. So in this, specifically in this study, we want to develop a geometric spatial temporal control co-design to maximize the power to weight ratio of the MCT and analyze the whole design from the ocean currents to power generation together. Okay, the first task here is to identify the main design parameters in our system. The main design parameters in our system are rotor diameter, buoyancy tank size, and generator rated power. So these design parameters, the first one is rotor, which affects the whole system design and power generation. By having a larger rotor, we can increase the power production from our system, but it also increases the forces and MCT weight. The second design parameter is buoyancy tank, which keeps the system afloat and also impacts its vertical movement. So by having a larger buoyancy, we can increase the bound or range of movement for our system, but it also increases the MCT weight and cost. The last design parameter is generator, which determines the power production from our system. By having a larger generator, we can increase the power production from the system, which is also related to the ocean current velocity, but it also increases the system size, weight, and cost. So we want to find a bidirectional coupling between this plant design and path control together, and we formulate a nested co-optimization framework, which includes two optimization loops. The outer optimization loop is responsible for optimal design parameters, and the inner optimization loop is responsible for path planning. We specifically show the objective function for the outer optimization loop, which considers maximizing the power to weight ratio. This optimization problem should be solved according to the constraints on the design parameters, which are generator rated power, rotor diameter, and buoyancy tank size. Then we also consider the maximization of power harness from the system, which is solved in the inner outer optimization loop. And we also consider the total mass for this system. This total mass is related to the mass deviation in the rotor diameter considering rotor diameter changes or the changes in the generator rated power and also buoyancy tank size. So we find the equations for this mass based on our experience for MCT system and also some reference equations from the wind turbine. Okay. Then I show the proposed framework here. From the proposed framework, you can see that the outer optimization loop is responsible for finding the optimal MCT design. It considers the design parameters as the variable buoyancy tank size, rotor generated, the rotor diameter, and the generator rated power. So at each iteration of this optimization, we just produce some population from these design parameters, and they are given to the inner optimization loop. So the inner optimization loop takes care of the finding the maximum harness power from this system, where we use the MPC algorithm to solve this optimization problem, and it is solved based on the constraints on the MCT linear model for the movement of the system, a spatiotemporal ocean currents model, and also operational constraints on the field fraction and also the operating depths of the system. So by iterating this optimization, we can find the optimal MCT design for our system. Now I want to show you the simulation results. Okay, so the first simulation is related to the sensitivity analysis for our system, where we consider the rotor diameter, generator rated power, and buoyancy tank size as main design parameters, and we want to identify the dominant design parameters between them. So from the results, we can see that the rotor diameter mainly changes the power to weight ratio. So it's the dominant design parameter, and it is somehow obvious for us because the power is squared with the rotor diameter, and if we have the bigger rotor diameter, it requires larger supporting infrastructure, including larger nacelle and a stronger mooring cable for our system. So finally, we compare the optimal MCT design for our system through two different cases. The first case is related to the baseline MCT design, which is already discussed in the beginning of the presentation. The second case is related to the co-design, only considering the rotor diameter as a dominant design parameter for our system. And the third case is related to the control co-design for multiple design parameters. So these results are shown in this table. You can see that in the first case, we have the rotor diameter of 20 meter, rated generator power of 700 kilowatt, and the buoyancy tank size. So we calculate the harness power from the system and power to weight ratio. So in the second case, we only consider changing in the rotor diameter, and we see by increasing the rotor diameter, the harness power from the system and the power to weight ratio are increasing. The last case is related to changing in rotor diameter, rated power generator, and also the buoyancy tank size. We can see that the optimal design values that are harnessed in this case are far from the design parameters in the baseline case. So this control co-design is necessary for our MCT system, and we can see that the power to weight ratio is increasing, and it is the optimal case among these two cases. So the average power to weight ratio versus time for these cases are shown in this figure. Okay, now I want to conclude the presentation and give you the future works to continue this current study. So in this presentation, I present a control co-design framework to couple the physical design and also spatiotemporal path planning and find the optimal power to weight ratio for the MCT system. As the future works to continue to study for the MCT system, we can consider presenting the path planning algorithm for the array of the autonomous MCT system. Also, we can expand the current study as the control co-design framework for the MCT to couple the physical design and the integrated path planning and tracking framework together. Finally, we can present the integrated path planning and tracking framework to avoid collision, and using the deep reinforcement learning algorithm, specifically proximal policy optimization, to address both path planning and tracking framework. I highly appreciate your attention in our presentation. These are the related publications from our group in the MCT area. Please do not hesitate to contact if you have any question. The contact information are given at the bottom of the slide. Thank you.